Every year, over 65 million tons of aluminum are produced worldwide, but only 4% of it is born in the heart of the desert, at the Emirates Global Aluminium plants. Here, amidst heat exceeding 1,200 degrees and power greater than that of small nations, metal travels a path from a gleaming ingot to the facades of the legendary Palm Jumeirah. Tens of thousands of tons are transformed into bridges, panoramas, and a light that never goes out. But behind this brilliance lies a story you haven't heard yet. Watch until the end, and you'll find out how this silver metal changed the face of Dubai forever. First and foremost, aluminum was used in the facade structures of hotels and residential complexes located on the fronds of the palm. It was chosen for its anti-corrosive properties. Unlike steel, aluminum naturally forms an oxide film that protects against moisture, salt, and ultraviolet light. The surfaces were treated using the anodic method, or powder coating was applied, creating textures that imitate marble, sand, or even mother of pearl, all to combine modern aesthetics with inspiration from nature. Emirates Global Aluminium is like an invisible engine that drives not only the industry, but also the landscape of Dubai itself. Their plant in Jebel Ali produces 1 million tons of aluminum annually, and the power station's capacity there exceeds 2,300 megawatts, like that of a small country. And the facility in Al Tawila in Abu Dhabi is even a third larger, 1,300,000 tons, and electricity, more than 3,100 megawatts. Together, these two giants produce almost 2,400,000 tons a year. That's approximately 4% of the entire global production. Palm Jumeirah, with its luxurious facades and bridges, literally lives on this metal. Some estimates suggest tens of thousands of tons were used just for the exterior surfaces, railings, lighting, and even balcony structures. It all starts with aluminum ingots, which arrive at the processing shop weighing 5,000 or 6,000 pounds each. These ingots from the smelters undergo an initial cleaning, where their surface layers are removed and they are prepared for melting. The melting furnaces operate at a temperature of 1,200 degrees Fahrenheit to turn the aluminum into a liquid, homogeneous mass. The liquid metal is poured into molds to create slabs approximately 6 inches thick, 20 feet long, and about 3 or 4 feet wide. The story of Emirates Global Aluminium is not just about numbers, it's also about over 330 different products, from sheet aluminum to forging billets. Aluminum with a purity of up to 99.96% goes into aviation, electronics, and architecture, as in the case of Palm Jumeirah. This island doesn't just consume metal, it demonstrates how it can be transformed into an environment where aesthetics and functionality go hand in hand. In addition to decorative elements, aluminum was actively used in window and balcony systems. The lightness of the material allowed for the creation of panoramic glass structures that offered views of the sea without overloading the building's foundation. Its thermal stability and ability to reflect solar rays helped reduce cooling costs, critically important in a climate where summer lasts almost all year round. After cooling, the ingots are cut into pieces convenient for rolling. Alloying elements are added to this: silicon, magnesium, manganese, to obtain alloys capable of withstanding ultraviolet light and sea salt spray for many years. Aluminum also became an integral part of infrastructure projects. Bridges between the fronds of the palm, service platforms, railings on the embankment, all of this is made from high-strength aluminum alloys. Its lightweight allowed for using fewer supports and assembling entire blocks faster without the need for additional cranes or heavy machinery. The next stage is rolling. The ingot is fed into rolling mills, where, under the pressure of rollers, it is formed into sheets with a thickness from 1/4 of an inch to 1 inch, as well as into profiles and extruded structures. These aluminum sheets can reach 15 feet in length and 4 or 6 feet in width, weighing up to 4,500 pounds for a single element. The roller of the rolling mill creates a hum. The metal is thinly drawn out, and emerges as a smooth, shiny surface. Now, anti-corrosion treatment. Aluminum has a natural protection in the form of an oxide layer, but for a marine environment, additional anodic oxidation is applied. The sheets are immersed in acid baths with a temperature of 100 degrees Fahrenheit, under a voltage of up to 25 volts. Thanks to this, a thick, transparent oxide layer forms on the surface, which makes the aluminum even more resistant to salt, scratches, and ultraviolet light. After this, powder coating is applied, especially on facade panels. A stream of powder heats the sheet to 350 degrees Fahrenheit, where the powder polymerizes, creating a matte or glossy finish that can withstand 5,000 hours of salt spray. Aluminum panels and profiles, each weighing 2,500 pounds, are packed onto special ramps inside containers. To protect against temperature and moisture, the container is maintained at a temperature of 75 degrees Fahrenheit. When the cargo is ready, trailers take it to the port, where it is carefully loaded into large volume containers. One container can hold 5 tons of aluminum in various components. The sea journey lasts 2 or 3 nights, and when the container arrives at the island, it is unloaded in special thermal zones. There, the panels are carefully removed, unpacked, and the markings are checked, namely the serial number, production date, and coating thickness. Installation. Aluminum facade panels, roofs, and decorative elements are attached to steel frames. For this, stainless steel bolts, rivets, or geodetic fasteners with an allowable deformation of 1/16 of an inch are used so that the panels can breathe under temperature changes. Workers at a height above the sea install HVAC guides, gutters, skylights, and ventilation openings, all made of lightweight aluminum. Special attention is paid to lighting. Almost the entire system of street lighting and decorative illumination is aluminum. Thin posts, transparent luminaire housings that do not heat up, have a long service life, and maintain their appearance even during sandstorms. Thanks to its electrical conductivity, aluminum allowed for the integration of intelligent elements, motion sensors, brightness changes, and synchronization with the overall smart city system. The installation schedule is impressive. 15 to 20 panels are installed daily, each 200 square feet. In total, approximately 9 million pounds of aluminum are used on the project. According to expert estimates, Palm Jumeirah required tens of thousands of tons of aluminum, especially for facades, balconies, lighting, and bridge structures. The exact figures are not disclosed, but considering the scale of the island, it is one of the largest projects in the region where aluminum was a key material. What truly makes Emirates Global Aluminium special is their approach to ecology and technology. They were the first in the United Arab Emirates to license their own smelting technology abroad. In their data centers, artificial intelligence has reduced energy consumption by 50%, and data processing speed has increased 35 times. They haven't forgotten about recycling either. At Al Tawila, they launched the Aluminium Recycling Coalition initiative to reduce their footprint and create a closed-loop production cycle. And all this so that the metal used to make beer cans can become the foundation for the most ambitious urban dreams in the world. In the evening, the surface area of the panels reflects the sunlight in such a way that the island appears almost crystalline. The aluminum shines with silvery planes, while the steel remains a stern foundation. It all began with a melting furnace and ingots, and ends with an architectural shell that both protects and impresses. Imagine this. Hidden right under your feet could be a mountain of old car tires. You'd think it's just rubbish, left to rot in a landfill for centuries. But what if I told you that this black rubber gets a second life and becomes the foundation for modern sports stadiums? Every single football field uses up to 40,000 tires. Now, multiply that by the more than 13,000 arenas in the US alone, and you get hundreds of millions of old treads, transformed from the road into a green carpet for athletes. How exactly new life is born from dirty scraps? We're about to break it down, step by step. Stick around till the end, and you'll uncover a secret most people never even thought to look for. So today, we're heading to a cemetery. A car tire cemetery. Acres of land piled high with mountains of black rubber rings. These are the silent veterans of the road, having done their thousands of miles, now lying here, seemingly useless. But this isn't the end of their story. It's just the beginning of their amazing reincarnation. We'll follow how these worn-out, dirty pieces of rubber go through a series of brutal, yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. This is the story of how the roar of the road turns into the quiet whisper under an athlete's feet. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the US is now over 85%. That's one of the highest rates for any consumer product. That means over 250 million tires a year dodge the landfill and are sent off for a new life. Some of them are burned as highly efficient fuel, some are used in civil engineering, but a significant and growing number are turned into that very same crumb rubber. In this tire cemetery, a machine that looks like a steel Tyrannosaurus Rex is at work. This is an industrial shredder. A huge loader grabs a whole handful of old tires and dumps them into the machine's steel jaws. Inside, two massive shafts with thick, sharp hooks spin with a deafening screech. They grab the tires with relentless force and, with an incredible crack, tear them to pieces. There's nothing delicate about it. The shredder's job is simply to break the tire's integrity, turning it into rough, palm-sized chunks. At this moment, the first important liberation occurs. Inside, every tire is a steel cord, a strong frame of steel wire. As the tire is torn apart, this cord is released, turning into a shiny web of steel threads mixed with rubber chunks. This chaotic mix of rubber and steel moves along a conveyor belt. And here, a powerful, massive industrial magnet spinning above the stream of shredded material comes into play. Like a fridge magnet, but 1,000,000 times stronger, it pulls all the steel threads from the rubber mass. With a screech and a clatter, the steel cord sticks to the magnet and is dropped into a separate container. This steel will later be sent off to be melted down, while our cleaned rubber continues its journey. But it's still too big and coarse. The next stop is the granulator. This is something like an angry coffee grinder the size of a car. Inside, sharp blades spin at enormous speed, chopping the large chunks into a smaller fraction, about the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire extra strength. These light, fluffy fibers need to be removed. To do this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have a clean, but still quite large material. To become the surface of a stadium, it needs to be turned into a crumb. For this, the granules are sent for final grinding, often in what are called cracker mills. These are two massive grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the tiniest particles. As a result of this process, we finally get what this was all about: crumb rubber. It's a uniform, free-flowing mass, like black caviar or coarse sand, where each particle is only a few millimeters in size. This crumb is carefully sifted to ensure a perfectly uniform size, and is packed into huge 1-ton bags. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now, let's jump to the place where this black crumb will find its true calling: the construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. This isn't just a green carpet. It's a backing with long, soft polyethylene blades sticking straight up. But for now, they look sad and limp, pressed against the base. For them to stand up and look like real grass, they need support. And this is where a special machine, looking like a large fertilizer spreader, drives onto the field. A process called infill begins. First, the machine spreads a uniform layer of fine, rounded quartz sand over the entire field. It's heavy and settles right at the base of the carpet, acting as ballast to keep the turf from shifting and helping to stabilize the blades. And following the sand, our main hero is spread onto the field, the black crumb rubber. The machine distributes it just as evenly over the entire surface, and here, the main transformation happens. This crumb fills the space between the blades, forcing them to stand vertically, just like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, springy rubber particles compresses, absorbing the impact energy. It's like running on a billion tiny trampolines. This drastically reduces the strain on athletes' joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and crumb rubber and brushing them deep down to the base, making every blade stand perfectly straight. And so, when the work is done, what stands before us is a perfectly green, resilient, and safe field. And none of the players running on it might ever guess that under their feet, between the bright green blades, lie millions of particles of old car tires that have completed their epic journey from the roar of the motorway to the quiet, springy surface of a sports arena, having received a second, much nobler life. To create one standard American football or soccer field, you need, on average, between 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats up a whole mountain of rubber waste. And how many of these fields are there in the country? Right now, there are over 13,000 artificial turf fields in the US, at schools, colleges, parks, and professional arenas. And that number is growing every year. Now for some simple maths. Even if we take the minimum figure of 20,000 tires per field, it turns out that over 260 million old tires have found their new home in the surfaces of sports fields across the country. That's almost a year's supply of all the rubber scrap the country generates. Natural grass is a very fussy thing. It needs to be constantly mowed, watered, fertilized, and given time to rest. On average, a natural field can handle no more than 20 hours of play per week. And an artificial turf field? It can operate 24 hours a day, 7 days a week, in rain or shine. Now, let's talk about water. A single artificial turf field can save from 500,000 to 1 million gallons of water every year. That's the amount of water an average family uses in several years. Add to that the savings on fertilizers, pesticides, and lawnmower work, and the benefit becomes obvious. So next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves a waste problem, makes sports safer, and saves precious natural resources, one old tread at a time. Imagine a magnet so powerful it can lift a weight 1,000 times its own. How can a piece of metal stop a jet engine turbine or become the heart of a Tesla electric motor? The secret lies in rare earth elements, materials that hide more mysteries than gold or platinum. To create a single neodymium magnet, you have to move mountains of ore, melt metal at over 2,700 degrees, and use technologies that resemble alchemy. But there's a detail that almost no one knows about. Watch till the end, and you'll learn a secret that will change your understanding of the power of metal. The mining and initial processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundations for obtaining the necessary components are laid. This process begins with the large-scale mining of ore, containing the rare earth elements that make up neodymium. In the first stage, the ore is extracted from the earth using various mining methods. This can be either open pit mining or underground mining, depending on the depth and type of the deposit. After extraction, large chunks of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size into smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed into mills for further fine grinding into a powder or a pulp, which consists of fine ore particles suspended in water. The next critically important stage is ore enrichment, the purpose of which is to separate the rare earth minerals from the waste rock. This process can involve various methods. One of the most common methods involves mixing the crushed ore with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a froth that is then collected. Heavier particles settle faster, allowing them to be separated from the lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After enrichment, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not a pure metal. It requires further chemical processing, which usually includes dissolving the valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the separation of each rare earth element individually and its purification to a high degree. For example, neodymium is separated from other rare earth elements like praseodymium or samarium. The final result of this complex chain of processes is the production of high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary to obtain the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most crucial stages in the production of high-performance neodymium magnets: alloying. This process demands extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy, providing its unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for instance, to increase the magnet's temperature stability, improve its resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret for many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important as it prevents the oxidation of the rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would degrade the magnetic properties of the material. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving a complete melt and homogenization of the alloy, the stage of rapid cooling, known as the strip casting method, begins. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating, cooled drum. Contact with the cold surface of the drum leads to an extremely rapid cooling of the melt at a rate of up to millions of degrees per second. This extremely rapid cooling prevents the formation of large crystal grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material takes the form of thin, easily crumbled flakes or ribbons. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for the magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be locked in during subsequent production stages. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron boron alloy have been formed, a stage called hydrogen decrepitation begins. Then there are two paths: either long-term dry storage in double-walled concrete containers or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Transportation is under guard on a special route with an escort, GPS, and mandatory 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark grey color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part, isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid. Basically, a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit, scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. Yellowcake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellowcake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby. The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellowcake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellow cake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade if you can find any. There are 2 ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video. Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or, far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material. But it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created 3 substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these 3 products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage: liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learn to obtain 3 extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet, all of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies. Every year, thousands of tons of fiberglass rebar are produced worldwide, a material that's throwing down the gauntlet to steel. Imagine, hundreds of spools of fiberglass, thinner than a human hair, merging into a single river, passing through sticky resin baths, red-hot dyes, and scorching ovens to be born as a rod that's 4 times lighter than steel, twice as strong, and completely immune to rust. This rebar is capable of doubling the lifespan of concrete structures and changing cities forever. But the most interesting part is hidden in the very heart of this process. If you watch until the end, you'll discover a secret that will completely change your understanding of the future of construction. It all begins at one end of a massive workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall several yards high, hundreds, and sometimes even thousands, of huge bobbins are installed in neat rows. On each of them is wound the finest glass thread, or roving. This isn't the kind of glass that windows are made of. This is a special fiberglass, produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. These will be our skeleton, our internal army that will give the rod its insane strength. From each of these hundreds of spools, its own separate thread is drawn, and they all come together into one thick, fluffy strand. It's like thousands of small streams merging into one large river. This dry, white strand is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. every one of the thousands of threads must be tensioned with the same force. If one thread sags while another is too tight, the load in the final product will be distributed unevenly and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: a baptism in resin. The dry glass strand is slowly submerged into a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat that will grow on the glass skeleton. It's a complex chemical cocktail. The base is usually a polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will trigger a chemical reaction and force the liquid to turn into a solid plastic. Various additives can also be added here. Pigments to add color, ultraviolet inhibitors so the rebar isn't afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to saturate every single, even the tiniest fiber. The strand must be completely submerged in this resin so that no dry spots remain. The saturated strand, heavy with sticky resin, exits the bath and heads to its point of birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round polished hole, the diameter of which exactly matches the diameter of the future rod. The die is heated to a certain temperature. When the wet strand is pulled into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass strands together, forming a perfectly round rod. Third, the heat from the die initiates the initial stage of the chemical hardening reaction, or polymerization. The resin begins to transform from a liquid into a gel. At the exit of the die, we can already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special strand of the same fiberglass is wound around it. A thin, resin-saturated thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled onto the sticky surface, which adheres permanently to the resin. Now, our rebar has not only strength, but also teeth with which it will hold onto the concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber that can extend for tens of feet, inside which a high temperature is maintained, usually 400 degrees Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively bond with each other, forming a strong, rigid three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material that permanently binds millions of glass fibers into a single monolith. It's like baking a pie. As the rod slowly moves through this hot tunnel, it acquires its final, rock-solid hardness. But what pulls it through this entire long journey, from the spools to the oven? At the end of the line stands a special pulling device, which gives the whole process its name. Usually, it's two caterpillar-like mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and pull it towards themselves at a constant, precisely calibrated speed. It is they that create the force that pulls the fiberglass through the resin bath, through the forming die, and through the oven. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor, an endless, perfectly straight, hard and hot fiberglass rod emerges. The final cord is cutting. An automatic saw is installed across the line. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward motion, and with a sharp zzzzt, cuts a piece of standard length, for example 20 or 40 feet, from the endless ribbon. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And just like that, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and ovens, have turned into a lightweight but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungle. The fiberglass rebar market is not yet a giant like the steel market, but it's the coolest and most audacious newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are just insane. It's expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now for the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sound boring? Now imagine this in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it's limited by weight. Or for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can easily carry whole coils or bundles of fiberglass rods, whereas moving steel requires a crane. This is a colossal saving in logistics and labor. Second is strength. And here, fiberglass just steps into the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing a regular rope with a climbing rope. At a smaller thickness, it can withstand much greater loads. But the main trump card, the real superpower of fiberglass, is its war against rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. The rust expands in volume and literally tears the concrete apart from the inside. Annually, the US spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years. And a structure with fiberglass rebar is easily designed for more than 100 years. Every year, over 500,000 tons of aramid fibers are produced worldwide, and the lion's share of that belongs to Kevlar, a material that can stop a bullet, withstand heat, and save lives. But how is a golden thread, 5 times stronger than steel, born from 2 unremarkable powders? In this video, we will dive into the world of chemistry, where stainless steel reactors boil, concentrated sulfuric acid rains, and every molecule is aligned into a perfectly parallel army. Watch until the end. You will learn a hidden secret that is usually not shown even in closed laboratories. It all begins not with fire and not with molten stone, but in the silence of a laboratory and in giant stainless steel reactors. We have 2 main characters, 2 chemical components that look quite boring. The first is a powder. The second is a needle-like crystalline substance called terephthalonyl chloride. This is our molecular Lego. Imagine that the first molecule has 2 hands, and the second has 2 hooks. The task is to make them hold hands and form an incredibly long and strong chain. This process is called polymerization. These 2 powders are loaded into a huge, perfectly clean reactor, and a special solvent is added so they can move and find each other. Then the reactor begins to stir, and here a chemical reaction takes place. The hands and hooks link up. molecule by molecule, forming a super long spaghetti-like macromolecule. The reaction releases a byproduct, hydrochloric acid, so the entire mixture becomes extremely aggressive and corrosive. After some time, the liquid in the reactor turns into a thick, viscous, honey-like mass of a golden color. This is no longer just a mixture, it's a polymer called polyparaphenylene terephthalamide. But this is not yet Kevlar, it's just its embryo. And here the first huge problem arises. This new polymer is incredibly stubborn. Its molecules are so straight, rigid, and strongly attracted to each other that in a solvent they immediately clump together, forming solid crystals. Our golden, thick mass is actually not a solution, but a suspension, similar to a gel, where solid particles float in a liquid. Trying to make a fiber from this is like trying to squeeze wet sand through a thin needle. It won't work. To turn this gel into something from which you can draw a thread, it needs to be completely dissolved. But how do you dissolve something that is almost insoluble in anything? For this, you need a super solvent. And scientists found it. It's concentrated sulfuric acid. Imagine, to tame this super strong polymer, you need to immerse it in one of the most corrosive and dangerous substances known to man. The thick polymer mass is carefully, with all safety precautions, mixed with cold, concentrated sulfuric acid. And a miracle happens. The acid breaks the weak bonds between the chains, forcing them to let go of each other and disperse in the solution. But most importantly, the rigid rod-like molecules of Kevlar in this solution behave not chaotically, like ordinary polymers, but form a so-called liquid crystalline solution. This means that they spontaneously align themselves into parallel groups, like logs floating down a river. This is a key moment. Already at this stage, while still being a liquid, the molecules begin to prepare for their future superstrength. Now this thick, viscous, resin-like liquid crystalline solution is ready to become a fiber. A process called dry jet wet spinning begins. The solution is forced under huge pressure through a special pot called a spinneret. This is a metal plate with hundreds of microscopic holes drilled in it, each thinner than a human hair. The solution is forced through these holes with incredible force, and on the other side, hundreds of the thinnest, shiny jets appear. But they don't just emerge into the air. First, they pass through a small air gap, literally a few millimeters, where they are slightly stretched, and the already partially ordered molecules align even more parallel to each other. And then these still liquid threads immediately enter a coagulation bath. This is a pool of cold water, or a special solution. When the hot acid solution meets the cold water, a sharp solidification occurs. The acid is washed out, and the polymer chains freeze in that perfectly ordered position they were in. Before our eyes, the liquid has turned into a solid, yet still flexible golden fiber. A whole tow of hundreds of individual fibers comes out of the coagulation bath. But it is still soaked with remnants of acid and water. Therefore, it passes through a whole series of washing baths, where it is thoroughly cleaned, and then through drying chambers, where all the moisture is removed from it. Now we have a clean, dry Kevlar fiber. It is already extremely strong, but this is not the limit yet. To achieve maximum performance, the fiber is subjected to a final test, thermal drawing. The tow of fibers is heated to a high temperature, 300 or 400 degrees Celsius, to make it slightly plastic, and passed through a system of rollers rotating at different speeds. The subsequent rollers rotate faster than the previous ones, which causes the fiber to stretch. This final stretching does something incredible at the molecular level. It eliminates any last imperfections in orientation, forcing absolutely all the long, rigid molecular chains to align in perfectly parallel lines along the fiber's axis. They are packed so tightly and orderly as is physically possible. all the force of billions of intermolecular bonds now works in one direction. It's like comparing a scattered pile of straws to a tightly twisted rope made from the same straws. It is this perfect order that gives Kevlar its legendary tensile strength. After this final workout, the fiber is cooled and wound onto huge bobbins. This is the final product, an endless, shiny, golden thread, soft to the touch, but capable of stopping a bullet. From these bobbins, it will later be woven into fabric for body armor, braided into ropes for suspension bridges, or embedded in composite materials for Formula One cars. And all this is the result of an incredibly complex journey from two simple powders to a perfectly ordered army of molecules, standing shoulder to shoulder, ready to withstand loads that seem impossible. The aramid fiber market, where Kevlar is king, is a global industry that turns over more than $3 billion a year. And this figure is constantly growing because humanity finds more and more ways to use this material where ordinary materials simply give up.